Let's study 10th standard ICSE Physics Chapter 1B and 1C, that is Center of Gravity and Uniform Circular Motion.
The first paragraph is entirely cancelled. Now imagine there is an object and we choose one point such that the total moments of forces of each and every particle on its left is equal to the total moments of forces of each and every particle on its right. You see, every particle has a weight, which is nothing but a force. So these have something called anti-clockwise moment of force or moment of weight, and these particles will create a clockwise moment of weight. What if the total anti-clockwise moment is equal to the total clockwise moment? Then we say that this pivot, this point, is indeed the center of gravity. So that's the definition of center of gravity, the point about which the algebraic sum of the moments of weights of all the particles constituting the body is 0. Because here the clockwise moments of forces will have negative values. Let's say -2 here, -1 here, -3.1 here. And the anti-clockwise ones will have positive values. Let's say 4 and 2.7 and 1.1 and so on. And if you add them up all up algebraically, you will say the net torque is 0. And hence this becomes the center of gravity. If I shift the pivot even slightly to the left or right, it is no longer in equilibrium, because then the total clockwise moments will not be equal to the total anti-clockwise moments. Center of gravity of an object is the point where we can imagine the entire weight of the body to be focused. We have to remember a few points about center of gravity. You see, the position of the center of gravity depends on its shape, that is the distribution of mass. Imagine you have clay of a particular shape which has a center of gravity here. If you change the shape of clay, now the center of gravity's position will change. You see, the total mass to its left should be equal to total mass to its right. The total mass above it should be equal to total mass below it, and so on. The total mass is same, but the distribution of mass changed, so the center of gravity's position also changed. Secondly, it is not necessary that the center of gravity has to be within the material of the body. For example, if you have a straight wire, then the center of gravity is at its midpoint. But what if you turn it into a circle? Now the center of gravity will be right in the center, which is not in the material of the wire, not in the copper material of the wire. So center of gravity can be outside the body as well. And you have to study this blue table, which has the position of center of gravity for some regular objects. For example, for a rod we just discussed, for a disc or a sphere, it's always in the center. What about a cylinder? Well, it will be at the midpoint of the axis of that cylinder. For a rectangle, parallelogram or square, it's just the point of intersection of the diagonals. For any triangular lamina, and by lamina I mean a two-dimensional plane surface, just draw the medians. It can be any triangle, even a scalene triangle. Draw the medians, that is the line joining the vertex of the triangle and the midpoint of the opposite side. So the three medians meet at a point, and that is the center of gravity. Now let's understand the center of gravity of a cone. If it's a hollow cone that is empty from the inside, then we can't say the center of gravity is at the midpoint of the axis. Clearly the mass above it is less than the mass below it. So actually the center of gravity is somewhere here. If you divide this axis into 3 equal parts, and if the total height is h, then the center of gravity is at a height of h upon 3 above the base. So that's where it is. So from top vertex, where would the center of gravity be? Well, at a height of, or at a distance of 2h upon 3. That's for a hollow cone. What if it's a solid cone, completely filled with some material like metal? Then we'll have to divide the axis into 4 parts. 1, 2, 3, 4. And so this distance is h upon 4. So the center of gravity is at a distance of h upon 4 from the base, or 3h upon 4 from the vertex. Center of gravity is very useful in understanding how to balance an object. If you want to balance something, we know that you will have to keep the pivot just below the center of gravity, so that the total clockwise moment is equal to total anti-clockwise moment. If we don't keep the pivot just below the center of gravity, if we keep it somewhere else, then it won't balance. It would just tilt in one or the other direction. That's one advantage of having the knowledge of center of gravity. But it goes beyond this as well. Now for this object, that is a bottle filled with water, the center of gravity is somewhere around here, deep inside, such that there is an equal distribution of mass around it. So you can topple it quite easily. Now consider this bottle with very little water in it. Where would the center of gravity be now? it would be somewhere around, let's say here, because most of the mass has been concentrated at the bottom of the bottle. So center of gravity has been lowered. So let's see what happens now. It's more difficult to topple it. You require a greater force. So this means that lower the center of gravity, more stable is the equilibrium of the body, and more difficult it would be to topple it. That's why wine glasses have a broad base, so that it doesn't topple easily because most of the mass is at the bottom. The bus conductor tells the passengers on the upper deck of a double-decker bus to remain seated to keep the center of gravity lower. Now, if I give you an irregular object, how would you find the center of gravity? Let's take this lamina of irregular shape. Just hold it and hang a thread with a needle from a point. Due to gravity, it will come to rest like this, vertically. Take a marker and draw a line along it. Next, you rotate this lamina, and again from another point you hang a needle with a thread. Imagine this is the surface, the earth. So again the string and the needle will come to rest like this, vertically. Take a marker and draw it. Similarly, from the third point you can draw the third line as well. And the point of intersection of these three lines will give us the center of gravity of an irregularly shaped lamina. We know what is uniform circular motion. Here the speed is constant, but it is an accelerated motion because velocity keeps on changing and there is a force applied here. So that's your give reason. Next, we have this sentence stating that the direction of motion or direction of velocity at each point is along the tangent at that point. The difference between the uniform circular motion and the uniform linear motion is that circular motion is always accelerated, whereas linear motion isn't. Now I said that whenever there is a circular motion, there is a force due to which the circular motion is possible. If this force did not exist, it would just fly away in a straight path. There is an inward force at each point, making sure that the object stays in this circular path. And that inward force is the centripetal force. For a stone tied with a string, that centripetal force is provided by the tension in the string. But what about an electron revolving around the nucleus of an atom? What provides that centripetal force there? Well, it's the electrostatic force of attraction between the negative electrons and the positive nucleus. And what about the planets around the sun or the moon around the earth? Who provides the centripetal force in this case? Well, it's gravitational attraction between these heavenly bodies. So you can see that centripetal force is a real force, and on the other hand, the centrifugal force is a fictitious force. What does that mean? Let's take an example. Look at this diagram. Here we have a merry-go-round. This is the axis of rotation. Let's say there's a pillar out here. This is the top view, of course. Imagine you are at A. So as this merry-go-round rotates, even you would rotate with it. There is a heavy ball at the periphery tied with the string to this pillar in the center. There is another observer, let's say M, who is an outside observer. So when the merry-go-round starts rotating, you would notice that the ball also rotates with it. But it doesn't fly out of the merry-go-round because it is tied with a string. You can notice that the string is taut. It's tight because there is a tension force acting, which is providing the centripetal force for the rotational motion of this ball. If this string breaks, the ball would just fly away along the tangent at that point. So an outside observer can clearly see the centripetal force acting on the ball, and it is directed towards the center of the circular motion. But when you are observing the ball from an inside point of view, you will notice that the ball is stationary, because as the ball moves, even you are rotating. So comparatively, for you, the ball is always right in front of you. When you are here, the ball is right in front of you. When you are here, the ball is right in front of you. So for you, the ball is stationary, which is quite strange because you can see the tension in the string. So you can see that there is a centripetal force being applied. So it is an accelerated motion. It's a circular motion. Even the outside observers will tell you that there is a circular motion, but you don't see any circular motion. You just see the ball in front of you. How do you explain that? Well, you conjure up a fictitious, a pseudo force called the centrifugal force, which acts outwards, which is equal and opposite to the centripetal force. And you think that because these two forces are equal and opposite, they will cancel each other, and hence the object is stationary for you. Note, the centrifugal force is not noticed at all by the rest of the universe. It is only a figment of your imagination to explain your observation. So that's how the centrifugal force is very different from the centripetal force. First of all, it is an assumed force, not a real force, and centripetal force acts towards the center of the circular motion, whereas centrifugal force acts away from the center of the circular motion. So this experiment's explanation has 2 points. One, what are the forces noticed by M? Only one, the centripetal force, the tension in the string. And what is the observation of A? Well, he takes into account two forces, the centripetal as well as the centrifugal, because only if he takes into account both the forces will he realize that indeed the net force on the ball is zero for him, and hence the ball is stationary for him. In fact, even when the string breaks and the ball flies away, you feel that indeed there was a centrifugal force. That is why the object is going away, because the centripetal force is no longer existing. So that's the difference between the two forces.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.